you so much. So this is a joint work with Ioannis, Caragiannis, and Nisarg, Shah, and it's about fairness in non-Centroid clustering. So what is non-Centroid clustering? Okay. All right, so non-Centroid clustering is similar to Centroid clustering, which means that we have data points in a metric space. But the difference with the Centroid clustering is that we don't want to select k centers and then to assign its data point to their closest center, but instead we want to partition the data points into k different clusters. So for example, here we have this metric space and we design that the orange points go all together in one cluster, the green points go to one cluster, and so on. So the high-level intuition goal that we want to achieve in a non-Centroid clustering problem is that similar individuals are assigned to the same cluster. So a reasonable question is how we can achieve fairness in this context. And actually, we'll use the idea of the core, which has been applied in committee selection and in the Centroid clustering work for defining fairness in the non-Centroid case as well. So what is the core? So just, I think we saw this before, but to remind you, so when we are in a committee selection problem and when we are in the approval case, and we want to select a committee of size k, then we're saying that the committee of size k is in the core if there is no a subset of individuals, and if there is no a subset of candidates, such that this subset of individuals can support to choose a subset of candidates, which means that the size of this subset is large enough. And this committee is not a Pareto improvement for the whole, for everybody in this subset of individuals. So in a very similar way, core was defined in the Centroid clustering problem, and here we define this in the non-Centroid clustering problem as well. And we're saying here, so first of all, we need to define what is proportionality in our world. So given that we have n data points and we want to create k clusters, every n over k individuals are eligible to select their own cluster. And so we're saying that a clustering solution, which is a partition of the individuals into k clusters, is in the core. You see I have an approximation here. I will talk about this very soon. We're saying that a clustering solution is in the core if there is no subset of individuals that is big enough, which means that has at least n over k, such that if they deviate and they form their own cluster, they are happier than they were before. And so this essentially is not a Pareto improvement for them. And so I have an approximation of alpha here because we will see that a solution in the core does not always exist. So we get an approximation with respect to how much they Pareto improve if they deviate. So it is a multiplicative approximation. So here you see that they have this loss function, which means that each individual measures somehow how happy they are when they are included in a particular cluster. So the question is, what is this loss function? So in this work, we consider two different, we believe, natural loss functions. The first one is the average loss, which means that the loss of an individual for a particular cluster is equal to their average distance to any other individual in the cluster. And we also consider the maximum loss, which is that the loss of an individual for a particular cluster is equal to their distance to the furthest individual in this cluster. So we consider these two different loss functions. And so we wanted to see what kind of approximations we can achieve with respect to the core with respect to these different functions. So first, as I said, the idea of core in Centroid clustering has been applied before by Chen et al. And they also defined an algorithm which is called greedy capture. And they saw that in the Centroid case, greedy capture provides a constant approximation to the core. So in contrast, in this work, we saw that under the average cost, if we use a variation of greedy capture, so we essentially adapted the greedy capture in a way that serves our non-Centroid problem. This provides a solution that is in the order of n over k. So here now we see that we don't have anymore a constant approximation. It's just something that depends on n over k. And this is constant with respect to greedy capture. So we know that this approach cannot give us something better than this. And then, so the question is this the best we can achieve? So the answer is we don't know. So the lower bound that we have is only a small constant. So we saw that we cannot achieve an approximation better than 1,3. So there is a huge gap here, and I think it's a very exciting, interesting question if we can really close this gap here, and if indeed there exists a solution that is in the constant core. And I think it is interesting here that Nisarg and I, for example, disagree. I believe that the solution in the constant core always exists. Nisarg doesn't believe that, so I think it's interesting to see that's the answer. But things are better with respect to the maximum cost. So we saw that in this case, grid capture provides a two approximation, which is constant. But again, we were not able to find any lower bound that shows that core is empty. So it might be the case that even in this case, the core is always, we can always find a solution in the exact core and we don't need an approximation. So this is another interesting open question. So we saw that the core is not, we cannot really have great guarantees. And so we consider relaxation of the core, which is called fully justified representation. And so fully justified representation in the committee selection world essentially means the following. So if we have a subset of individuals that is, again, large enough, which means that they can support to choose a different set of candidates, and if the utility for all of them for this particular committee is at least a factor beta, then at least one individual from this subset should have at least utility beta for this the committee that we have selected. So committee satisfies FJR if whenever there exists another subset where all of them get utility at least beta, then at least one should get utility beta by the current committee that we have returned. And so we use this idea for defining FJR for non-centroid clustering. And so similar as the core, it's a subset of individuals that has size at least an uppercase eligible to deviate to their own cluster. And so if all of them have lost less than beta if they create their own cluster, then for the current solution satisfies FJR if at least one of them has a loss no larger than beta for the cluster that they currently belong. And again, here we have an approximation with respect to this fairness notion. And again, we consider the two different loss functions, the average loss and the maximum loss. So in this case, for the committee selection, we know an algorithm from Peters et al., which is called pretty cohesive algorithm, which shows that an FJR solution always exists. And essentially, a variation of this algorithm shows that an FJR solution in the non-centroid clustering world always exists as well. A problem with this algorithm is that it's not polynomial time, strictly, and it'd be hard to find to implement this algorithm. And so it is a reasonable question, what can we achieve with the polynomial time algorithm? And so we saw that if we apply greedy capture, which in our setting is polynomial time, then greedy capture returns a cluster solution that satisfies 4 FJR, so an approximation of 4 with respect to FJR. And when we are in the maximum cost case, it satisfies, it returns a solution that satisfies 2 FJR. And of course, an interesting open question, I think both in the committee selection problem and in non-centroid clustering, is if there is a polynomial time algorithm that achieves FJR. Okay, and I want to conclude with a reasonable question that you might have, like, why do we want the core into non-centroid clustering, and why we don't just consider classic objectives like K-median or K-means or K-center? So K-median essentially tries to minimize the within cluster sum of distances. K-means try to minimize the within cluster of the square of distances, and K-center essentially finds K different centers and then assigns each data point to the closest center. They try to minimize the maximum distance that each individual have their own cluster center to their closest cluster center. So these are very classic objectives and very traditional vanilla algorithms. However, we can see that in the non-centroid clustering world, they can be quite unfair from a proportional fairness perspective. So, for example, consider this case where we have this metric space, so which means that almost half of the individuals are in one position, on the same position on the metric space. Then almost the remaining half of the individuals are in a different position, which is relatively closer. It is relatively close to the first position, but it is very clear that these are two distinct cohesive groups. And then we have two outliers that they are very far away in the metric space, very far away from any. And so let's imagine that we want to create three clusters. Then if we apply either k-median or k-means or k-center, the solution that we will get is that we use two of the clusters for clustering the two outliers alone. And then we use the last cluster for clustering all the remaining individuals together. But I think we can agree that this doesn't seem very proportionally fair because these are two very distinct groups that are very large and they deserve to have their own clusters. And so if we apply for the CR, we will get essentially a solution that looks like this, where it distincts the two big groups and captures the outliers together. So to some extent, core is also more resistant to outliers. And I would like to conclude with that. Thank you so much.
So we do have time for questions.
Thanks, Evi. One question about this last example that you gave that motivates the core, for example. If you just restricted yourself to balanced clusters and then you took k-means, etc., and so on, that would not be a problem in this specific example.
Not in the specific example, but you can find other examples that you have the same problem. And since you mentioned this about this balancedness, so the variation of the gritty capsule that we consider in our project also returns balanced clusters, which we believe it is. We get this for free, and I think it's a nice property that we have.
Thanks.
What happens if the loss functions is, let's say, p-mean instead of average?
Interesting question. I believe that for general p-value,
The question.
yes. So what happens if the loss function is a LP norm in general? I guess that probably for different values of p, we will have different answers.
Because you have two extremes.
Yeah, right. I think that's an interesting question. I'm not sure. Yeah, I don't have very clear intuition about this.
I also have a question. Is there some, so like you said, the core is harder than justified representation. And there's also two in committee selection. How do you trade off, like, for example, if you have an algorithm which gives you a two approximate core, which is a stronger versus justified representation? Is there some systematic way to think about which one would you prefer?
That's an interesting question. So what, for example, if two core, for example, is better than one of JR?
Better, I mean, which one would you choose? How should one think?
How do you compare?
Yeah, that's it. How would you think about it?
I think it depends on the application. Yeah, and what we want really to achieve. I think I would personally prefer two core because two is probably a good approximation of the metric space, but I think it's not very obvious what the answer is here and what we want to achieve.